So we should wait for a couple of minutes more for people to come.
Yes.
Okay.
I have uploaded in the Slack channel a zip file that contains essentially the second part of the presentation, where we will implement the method by utilizing a Google Colab notebook. So please download the zip file. Okay, I think it's time to start. Hello, my name is Christoph Lefteris, and I'm a PhD student in the SimEA project. Today, I'm going to give you an introduction to multiscale modeling and present you a machine learning approach for backmapping coarse-grained macromolecules. We will start with an introduction to multiscale modeling and an overview of the bug mapping method. After that, we are going to implement the bug mapping method by utilizing a Google Colab notebook. Here we can see the time and the length scales involved in macromolecular complex systems. For the chemical bonds, we observe bond vibrations in the order of 1 femtosecond. Moreover, when we increase the number of bodies we observe, the characteristic times become much larger. For example, if we can see for the ankle and dihedral rotations. Then, if we observe the times related to larger parts of the chain, like here, the relaxation time can be in the order of 10 to the -8. And for polymer interfaces, the characteristic times can be in the order of days or even years. And because of that, it's not possible to utilize a single method to study this kind of systems. And this is a core of the multiscale modeling. Multiscale modeling of polymers exchanges information between coarse and fine representation of molecules to capture material properties for a wide range of spatial and temporal scales. One hopes to develop an approach that shares the efficiency of the macroscopic models as well as accuracy of the microscopic models. This figure here illustrates the scales where we study molecular systems. We begin with the quantum chemical level, where we derive the empty potentials. Then we go to the atomistic level, where we perform the atomistic simulations. And then we have the coarse-grained level, where we decrease the degrees of freedom in order to be able to access larger length for the time and length scales. And finally, we have the continuum level. In this presentation, we will focus on the coupling between the atomistic and coarse-grained levels. We continue with some details about the atomistic and coarse-grained descriptions. The figure on the left shows a chain at the atomistic description, and the figure on the right shows the same chain at the coarse-grained description. As we can see, the number of coarse-grained particles are far less compared to the number of particles of the atomistic description. This happened because we utilize an operator to decrease the degrees of freedom. Usually, we utilize a linear operator to do that. The most commonly used operator is the center of mass, where, for example, we place a coarse-grained bit at the center of mass of each monomer. At the atomistic description, we can compute the probability of a state Q at temperature T with the Gibbs canonical measure, where Z is a partition function and Kb the Boltzmann constant. Moreover, we can compute the force exerted to the jth particle by utilizing this equation here. Similarly, for the coarse-grained description, we can compute the probability of a state Q at temperature T with the Gibbs canonical measure. Furthermore, the embodied potential of the mean force can be calculated by this equation here. We have to note that the computational cost of calculating this quantity is still very high. Hence, we want to find an effective potential function that best approximates the PMF, which is easy to formulate and calculate. By defining the pairwise distance Rij, we are able to write the main embodied potential of the mean force in this form here. Moreover, we assume that the two-body effective pair potential approximates the PMF. Hence, we end up with this relation here. Here we can see some parameterization methods for coarse-grained models. Each one of these methods has a different observable. For the Boltzmann inversion method, we have the distribution functions. For the force matching method, we have the forces. And for the relative entropy, we have the microscopic probability distribution. Then we continue with the backmapping problem, where we reinsert the atomistic detail to the coarse-grained models. We have to note that this is an ill-posed problem, because when we go from the atomistic description to the coarse-grained description, the transformation is uniquely determined. But when we go back from the coarse-grained description to the atomistic description, the transformation is not uniquely determined. Hence, for one coarse-grained description, we can have many atomistic descriptions. If you have any questions so far, please unmute your mic and ask. Okay. We continue with the backmapping method. Here we have the original publication for the method. And we start with a brief abstract. We will demonstrate an efficient and versatile machine learning approach for backmapping coarse-grained macromolecules. It's an image-based approach for inserting atomistic detail to coarse-grained models. Through machine learning, we train a conditional generative adversarial network on the correspondence between configurations at the levels considered. And finally, we utilize the trained model to get predictions of atomistic structures from the input coarse-grained configurations. For the image-to-image translation, we utilize a general purpose conditional GAN. Where the coarse-grained configurations were employed as input and the atomistic counterpart served as ground truth. The conditional GAN contains two different networks. The discriminator, which classifies samples as real or fake. By real, we mean the target images, and by fake, we mean the generated samples from the generator. And then we have the generator, which during the training learns to fool the discriminator. On the right, we can see some applications of the conditional GAN. We continue with some details about the loss functions of the two networks. The discriminator loss function contains cross-entropy loss between predictions and the matrix of zeros, plus a cross-entropy loss between targets and the matrix of ones. And then for the generator loss, we have a cross-entropy between the predictions and the matrix of ones, plus a weighted L1 difference between the predictions and targets. And for the total loss function, we have the sum of the two losses above, which gives us this equation here. Here we have some details about the dataset we utilize to implement the method. We have a system with 96 chains and 30 monomers per chain, with a total of 61 configurations. Here we can see the total number of particles we have per frame. Our system contains 3 different monomer types. We have a cis monomer type, a trans monomer type, and a vinyl monomer type. The red dot denotes the center of mass of each monomer type. And we can observe that we have 4 united atom particles for every monomer type. And the dashed lines denote the connection between the monomers. For the coarse-grained configuration, bits are placed at the center of mass of each monomer. Here we have some notations about the figure we have on the right. With CC, we denote the center of mass of the chain, and with RI, the relative position of the monomer center of mass with respect to the center of mass of the chain. To perform the XYZ to RGB coordinates transformation, we place the vectors inside the reference unit cell and then utilize this equation here to perform the transformation, where L is the length of the unit cell and O the center of the cell. The purpose of this transformation is to rescale the values to integers in the interval between 0 and 255. Moreover, to identify the different monomer types, we place a unique color stripe before and a unique color stripe after every monomer representation. For the cis monomers, we have a black color stripe. For the trans monomers, we have a white color stripe. And for the vinyl monomers, we have a gray color stripe. We have to note that we utilize an image size of 256 by 256 pixels per image. Now let's see some details about data representation. For this scheme, we take the relative positions of the united atoms with respect to the monomer center of mass. We call those vectors VI. We can calculate these vectors by utilizing this equation here, where with Ci we denote the coordinates of particle I, and with theta and j the coordinates of the monomer J center of mass. We have to note that this scheme does not contain any information about the connection between the monomers. On the right, we can see a small sample of a target image and an input image. For the target image, we have the united atom representation of a chain which contains the information about 30 monomers. And for the input image, we have the representation of the coarse-grained description, which contains again the information about the same chain. If you have any questions so far, please ask. Okay. Okay, here we have an example of a monomer representation. As I said before, to identify the monomer type, we place a unique color stripe before and after every monomer. For this scheme, we have 3 vectors. Hence, we have 4 unique color stripes. As I said here, this image contains 30 monomers. Hence, we have 30 representations like this. Here we have a gray color stripe. And if we go back here, we can see that we have a vinyl monomer type. Now for the decoding procedure. Essentially, we mean the calculation of the WI vectors, which are the coordinates, the reference coordinates with respect to the chain center of mass. Actually, this is pretty simple to calculate. We just add the R vector to the VI vector, where the R vector is, contains the relative position of the monomer center of mass with respect to the chain center of mass, and VI are the vectors we encode into the image.
Sorry, Lefteris?
Yeah.
If you go to the previous slide, so
Yeah.
just to make sure the one with the colors. Yes. So we want to go from the coarse-grained to the atomistic. So each color represents a monomer.
Okay.
Or is it an atom?
Yeah, if you see, for example, right here, for this scheme, for every monomer, we have 4 vectors, 4 VI vectors, right?
Mm-hmm.
Okay, so we put this information inside the images we have here, but we place a unique color stripe before and a unique color stripe after every monomer representation in order to be able to identify the different monomer types. Now for the coarse-grained representation, we save only this vector right here, which is the relative position of the monomer center of mass with respect to the chain center of mass.
Okay, thanks.
Okay. Here we have a small sample of the bond angles, bond lengths, and dihedral angles distributions. As I mentioned before, this scheme does not contain any information about the connection between the monomers. Hence, for example, in the first image, we have a CC-CT bond, which connects a cis monomer with a trans monomer. And we can see that the target distribution is not able to capture the original distribution. Now, if we go to the second image, we have a CC-CDC bond length, which is inside the cis monomer. And as we can see, we have almost a perfect match between the target and the original distributions. Now for the dihedral angles and bond angles, the original and target distributions are very close. And we observe some pretty good results for the predictions for both the dihedral and the bond angles. Okay, if you have any questions, please ask.
So you said you have almost perfect match between the CC and CT?
Right here, you mean?
Yes.
Yeah, because it's inside the monomer. It's this mod length right here.
But the lines don't seem to...
Yeah, I mean about the original distribution and the target distribution.
Oh, okay, okay. Thanks.
Okay. Okay, that's it for the presentation. Here we have some references. The first publication is the original paper of the method. And this here is a paper about the image-to-image conditional gun we utilize to implement the method.
On your previous slide, what is prediction?
Prediction is a predicted coordinate from the conditional gun, from the network.
Okay. So you are trying to predict the original or the target?
The best results we can get, it's the target distribution, but eventually we want to target the original distribution.
Okay.
So I have uploaded a zip file in the Slack channel about the second section of the presentation. So please download the zip file. It may take a while, so I think it's a good time to take a 15-minute break, maybe.
Yeah.
Okay.
Lefteris, just one. Can you explain one more time the differences between the original of the target and the prediction in your figures?
Yeah.
So which one is the coarse-grained? Which one is the atomistic? And
no, it's all in the unit atom representation. So when you utilize a data representation scheme, you don't expect to get the same coordinates as the original frame. Imagine you have the transformation from the XYZ to the RGB coordinates and then go back to the XYZ coordinates. So by converting the values from floats to integers and then back to floats, you get a round of error. So this is why we have these different shapes for the target and original distributions. Okay.
okay, thanks.
Is it clear?
So the prediction is a prediction of the SIGAN.
Yeah.
Okay, and the original is from your original data set, and the target comes when you process your data set.
Yeah, exactly. Yeah.
Okay, thanks.
Okay, now let's continue in 10 minutes, I think. If you are back, please raise your hands.
Sorry, I did not hear, Lefteri, I didn't hear you. Did you ask for something?
No, just if you are back to raise your hand.
Ah, okay.
Okay, have you all managed to download and unzip the zip file? Okay. I think we can continue. Now we continue with the implementation of the method. To do that, we will utilize Google Colab. And just first, you have to open Google Drive. And then just press the plus sign right here and upload the folder to unzip. It might take a couple of minutes to upload. I don't know, Christos, can you hear me?
Yes, Lefteri.
Should I wait for them to download the folder and then upload them, or not?
Where is the folder now? So it's in a zip file, right?
Yeah.
So I guess so. Yes, that would be, I guess, the best way to.
Yeah.
To avoid this working on the same notebook.
Okay. So when you're done uploading the file to Google Drive, please raise your hand.
Let me first lower your hands.
Okay.
do we do anything after the folder is uploaded in our Google Drive?
I just wait for all of you to upload the file first, and then you just go to the SimEA Training folder, and then open the notebook, the polyremap notebook right here.
What do we open again? Excuse me, Lefteri.
Yes.
What do we open again?
Okay, if you manage to upload the SimEA training directory, then open the directory and open the double click on the polyremap notebook.
Polyremap. Okay, thank you.
Okay. I think I should start. First, we have to mount the Google Drive folder. To do that, we execute the first shell. And connect to Google Drive.
How did you open that?
What?
The Colab Research Google.com. I might have missed something before.
I just Google Drive, and should I send the link? I don't know.
I can double click on the iPy notebook.
Yeah, I think the question is, how do we open the notebook? Because I'm trying to also use something, but it doesn't work.
Yes, it is asking me of what program should I use to open the file and stuff like that.
You should go to, you should get some options, right? And there should be an application to connect called Google Colab. So it should be like this. So if it's the first time you use it, So it asks you to select with what default application to open the kind of unknown file until now. So you have to say what to use.
Okay, I think you right click, you open with connect more applications.
Yeah, I think
And then collaboratory.
Yeah, maybe you have to do that first. Yeah, I'm sorry. You press the plus sign and then more, and then go to Google Collaboratory. And then you should be able to double click on the notebook and utilize Google Colab.
Okay, indeed.
Okay. Okay, now try to mount to execute the first cell. Here we have a figure that illustrates the workflow for the backmapping method. First, we generate the images. Then we develop the conditional GAN, which we then utilize to get predictions. And finally, we analyze the results. Here we have the contents of the notebook. Did you all manage to open the notebook?
I did, yeah, it works with the collaborator.
Okay.
It asks for an authorization code.
Yeah, if you have a Google account, it will ask for permission actually, and
It is not our password, is it? No. Ah, okay.
just press on your.
Yes.
Okay.
Okay.
Okay, here we install some Python modules. And then we import the needed libraries for the task. Now in this cell, we load, let's call it a chemistry file, which contains the chemical structure of the system. By chemical structure, we mean the sequence of the monomer types. As we can see, the chemistry file shape is 96 by 30 because we have 96 chains per frame and 30 monomers per chain. Here we load the trajectory file, which contains 61 frames. Then we will utilize this function here to perform the XYZ to RGB transformation. where L is the length of the reference unit cell of the vector we want to perform the transformation. Then we want to create a unique image tag for every image. To do that, we utilize this function here, where I denotes the frame index J, the chain index, and end chain, the number of chains per frame. So as I said in the presentation, for every monomer type, we have a unique color stripe we place before and after every monomer representation. To do that, we use these functions here. For the cis monomers, we place black color stripe before and after every monomer representation. For the trans monomers, we have a white color stripe. And for the vinyl monomers, we have a gray color stripe. Moreover, these functions return the C list, which contains the lengths of the reference unit cell for each vector of each monomer type. If you have any questions, please unmute your mic and ask. Okay. Here we define the function that generates the images. The first array here, which is of a shape 256 by 256 by 3. It will contain the information about the atomistic description. And then here we will place the information for the coarse-grained description. And finally, for the R-tot array, we will pack both the atomistic and the coarse-grained description information. So here by utilizing an MD-Trach module, we get the length, the dimensions of the simulation box. And then we iterate to compute the coordinates of the monomer center of mass, of each monomer center of mass, and then be able to compute the coordinates of the chain center of mass. We have to note that we save the coordinates of the chain's center of mass inside this file here, because we want this information to be able to combine those images back together into the atomistic frame. So here, actually we save, as I said before, the R vectors are the coarse-grained coordinates with respect to the chain center of mass. So we calculate those coordinates with this equation here. By utilizing the chemistry file we load before, we get the type of each monomer, and then we use those vectors, those functions here to paint, to fill in the identity stripes and get the C list. Finally, we are able to compute the RGB values for the relative positions of the united atoms with respect to the monomer center of mass with these 3 lines right here. And here we we get the images. Is it clear so far? Okay. So now we are able to get some images. We choose the 20th frame. We expect to get, we save them inside this directory right here. So, no, it's not clear. Okay. We expect to get 96 images. Moreover, we want to calculate to get the original frame coordinates for this frame in order to be able to compare the results with the original coordinates. And now we continue by developing the conditional GAN. First, we load the images. As I said before, one image contains both the input and the real images. By real, I mean the target images. This function here separates those 2 images. And then we normalize the values of the images in the interval between -1 and 1 to speed up the calculations. And now we continue with the generator. For the generator, we have a UNet architecture. So if you are not familiar with convolutional neural networks, so it is what it is. I mean, you get an input shape, then you decrease the shape of the input until you hit a bottleneck, and then you increase again the shape until you have the same shape as the input shape. To do that, we utilize a downsample layer, which has a convolutional layer, a batch normalization layer, and a leaky ReLU activation function. And for the upsample layer, we have a transpose convolutional layer, and batch normalization layer. We add a dropout layer here and a ReLU activation function. Here we have the whole architecture of the generator. Then downsample layers, we have 8 downsample layers and 7 + 1 upsample layers. For the last layer, we utilize a tanh activation function in order to get values between -1 and 1. Do you have any questions so far? Okay. Now let's continue with the discriminator, which classify the samples as real or fake. For the discriminator, we have a patch-can architecture. By patch-can, we mean that in order to classify the image as real or fake, we take only a part of the image to do that. I think for this network, it's about 70% of the image. And here's architecture. Okay. We move on to define the loss functions for the networks. For the discriminator loss function, we have a cross-entropy loss between the discriminator real output and the matrix of ones, plus a binary cross-entropy loss between the discriminator generated output and the matrix of zeros. And now for the generator loss, we have a binary cross-entropy between the discriminator generated output and the matrix of ones, plus a weighted L1 loss between the target images and the generated images, the predicted images. Now, for the optimizer, we utilize an Adam optimizer for both the generator and the discriminator. Here are the parameters of the optimizer. In this cell, we restore the pre-trained generator, the weights of the generator we are going to use. And now we are able to get some predictions. So on the left, we have the input image we gave to the generator, which contains the coarse-grained representation of a chain. Then in the middle, we have the target image, which contains information about the united atom representation of the same chain. And on the right, we have the predicted image from the generator. As we can see, the target and the predicted images are very close. We can observe some blurring at the edges of the image, but I think that's okay. Now we continue with the backmapping process, where we reinsert the atomistic detail to the coarse-grained configurations by extracting the information from the predicted images. We will utilize the first function to perform the mapping from the RGB coordinates back to the XYZ coordinates, where L again is the length of the reference unit cell. Then with these two functions, you get a unique tag for the files where we are going to save the target and the predicted coordinates for the chains. And with this file here, we get a unique tag for the chemistry file, where we are going to save the chemical structure of the frame. Okay, these functions here helps us to name the unit atoms of each type. And finally, this function here calculates the sequence of the monomer identities of each chain. Okay, now we are able to perform the back mapping. Here we have some notations. With chain len, we have the number of unit atom particles per chain. With mer len, we denote the number of unit atom particles per monomer. With nmer, the number of monomers per chain. With nchain, the number of chains per frame, and with n part we have the total number of unit atom particles per frame. Now we iterate over the images we create before. We get the prediction from the generator. We create the unique tag for the files. We calculate the chemical structure of the chain. And then we continue by calculating the predicted coordinates from the image. Actually, here we have the RGB coordinates. We didn't perform the transformation yet. And here we have we get the information about the coarse-grained coordinates with respect to the chain center of mass. We continue by calculating the target coordinates from the target image in order to be able to compare the predictions with the targets during the visualization of the results. And here we calculate the XYZ coordinates for both the target and the predicted images. So this might take a while. I think it will take about 3 to 5 minutes. So if you have any questions, please unmute your mic and ask. If we go back to the data folder, we can see that we generate the coordinates. We expect that we will get 96 files, which actually is 96 chains, both predicted and target coordinates. So is it clear so far how it works? I guess it's not key. After this run finish, we are able to combine the predicted chains to get the atomistic configuration. To do that, we load the file which contains the center of mass for every chain of the frame. And then we simply add the center of mass of the chain back to the coordinates to get the global coordinates of the unit atoms. I see Christos posted some links about the unit architecture in the Slack, so you can have a look if you want. Actually, Christos, you can tell us about the form right now. I think we have a couple of minutes till
Okay.
Okay.
Sure. So same procedure as yesterday. You can spend a couple of minutes to fill in the form. Let me. I will copy it in the Zoom chat here and also in the Slack chat. So please spend 1 or 2 minutes to fill it in, and then at the end you will see again the Google form to put your name if you want to receive a certificate of participation. So let's wait a couple of minutes, and then so that people can fill it in, and then we can continue.
Okay.
The reason we are asking you to do this now is that if you don't do this within the training session, the probability of doing it afterwards falls almost to 0. So that's why we would like you to do that now.
I believe this link is it says day 2, but it has questions about DFT, which was yesterday. So I'm not sure if it's the right form.
Indeed, it's yesterday's form.
Christo?
Yes, I can hear you. Sorry.
Okay.
So just please mentally replace 1 with the morning session and 2 with the afternoon session. I'm doing it. I'm also changing the names now.
Okay, maybe we can proceed until you finish the form.
I would suggest just to fill it in, just replace row 1 with in your head with molecular dynamics and row 2 with backmapping. It will be ready in 1 second, so you can start filling it.
Okay.
Give me 1 second. Okay, probably now you will just see the regular names. So the names used for today. Did anyone get the chance to fill the form? Okay, Lefter, I guess we can continue.
Okay. Now, if we go to the data folder, we can see actually go at the end. Okay. So here we have and that file that contains the target coordinates for the frame. Sorry. And then GROMAX file, which can then utilize to perform molecular dynamic simulations. Now we are able to load, to visualize the results. To do that, we load the target frame, the predicted frame, and the original frame. And by utilizing the plot distributions function, we plot the bond length, bond angle, and dihedral angle distributions. As we can see here, we have for bond lengths, we have 18 combinations. For bond ankles, we have 27. And for dihedral ankles, we have 42 combinations. Okay, now let's go and see some results. We can go to, let's go to bond lengths. So here we have the same distribution as I have shown in the presentation. We have a CC bond length, which connects a cis monomer with again with a cis monomer. As we can see, the target distribution it's not very close to the original one. But when we go to this distribution, for example, we can see but for the CC single symbol length, which is inside the cis monomer, we have almost a perfect match between the target and the original distributions. I think now you are able to try some to create some frames by yourself. If you go back to where we generate right here, if you go right here and change the frame you want to generate, you may get some results by yourself. But before you do that, you just have to recreate, let's say, the val and data folders. I think I will give you about 15 minutes to try the code by yourself and ask me if you have any questions. So before you do that, you have to remove the folder and then recreate the folder, the same code for the data folder. Okay, I think, yeah, try it yourself. And if you have any questions, I'm here. So, yeah.
Sorry, can I ask something about the feedback form? Christo, are you here?
Yes, go on.
I see, I don't know if I have the right one, but I see that it says day 2, but it has the name of the courses of yesterday's event. Is it?
It's that one. Can you maybe refresh? I updated the names there now.
Okay.
Maybe if you refresh, you will see the updated names.
Okay. Yeah.
Yeah,
Sorry.
okay.
Yeah, thanks.
No worries. Hello, everybody. I will stop the recording now. So since we reached the end of the afternoon session, as I understand, Lefteris will stay online in Zoom and in Slack for some more time. So if you have any questions, you can ask him. And yeah, with this, thank you all for participating. I hope you enjoyed it. Please fill in that feedback form so we will improve the sessions for you the next time. And yes, that's all. Thank you very much.
Thanks a lot. It was a great event.
Thank you.
Thank you. Thank you very much.
Thank you very much.
Thank you.